4 hours. Then if you set in the autofocus with that too, your map now takes 27 hours. And it keeps building and building and building. And in here is the minimum pixel overlap. We always recommend you leave it at least 100. That's for when you do the actual multi-window mode. So in a single shot you can see 500 pixels. So for example, the first scan will go 0 to 500. You see that in a single shot. The second scan will go 400 to 900. Because then it'll leave those 100 pixels in the middle to overlap to help even out your baseline and your data as it stitches it together. Because it needs a point of reference. Now granted, if you use the multi-window mode though, the multi-window mode does not work well when you have something that fluoresces. Especially something that has a fluorescence that changes over time as you're going through a type of fluorescence absorption or something like that. Because every second that your sample's in the laser power, the fluorescence level will change some.
Right.
So when it goes to the next window, the intensity of your background has already went up or down by a couple hundred wave numbers, or a couple hundred counts, sorry. And then it won't be able to overlap it nicely. It'll just leave your data separated and kind of draw a diagonal line going up to attach it. So it doesn't work too well with fluorescence. And that covers our little multi-window. We'll put this back to single window mode right now for everybody else. Next, acquisition, extended range detector. Here in detector, this represents your CCD detector chip. It shows you what your chip is set for, the temperature, which pixels you're using, and everything else. I recommend, other than the temperature in here, which is at the bottom of the window, that you don't change anything. If you know a tornado's coming and you need to power the whole system off, you would open this detector window to warm the detector.
Okay.
Down at the bottom, it says TC. Right now it says minus 69.7. Most labs usually are anywhere between 20 and 24 degrees. So if I was to shut the system down to warm it up, you would open this detector window for shutting the system down, and you come in here and you would actually set this number to 20 and then hit set. And then you would leave this window open and monitor the detector temperature until it gets to positive 20. Once it hits about positive 20, the detector then is safe to power off. If you come in and the system is all powered off and everything is turned off, as far as the other devices around, you just walk around, click power switches. You know, turn the computer on, the controller on, the laser on, CCD on. There's no real rhyme or order to them.
Okay.
Just click them all on. But once you bring the system up from off, you would have to open this detector window, and again come in here in the temperature and type in minus 70, and then hit set.
Okay.
And then the detector will stop at minus 69. It doesn't actually stop at minus 70. Once it hits minus 69, the detector is safe to use. The detector actually is good to use even if it stops at, like, once you're at minus 55, the detector is pretty stable. But you don't want to use it until the temperature stops moving. As your detector gets really old, you might find, 10 years from now, it might stop at minus 60. It's still good, you can still use it. But you want to make sure the detector is fully cooled and is stabilized at that point before you use it. Because otherwise, as the detector cools more, you'll see your background and signal go down or up, depending on what you're looking at. They're using from the first pixel to the 1024th pixel, and in here we're using from 107 to 147, because that is where the data falls across your chip. So we shut off the first 100 pixels and the last 100 pixels to help the signal to noise ratio, and we only use the 50 pixels in the middle. Autofocus again, this here is for your autofocus device. You can set the range you want it to move, minus 45 to plus 45. The full range of this, I believe, is 100 is the max it can go. But to save time in your autofocusing when you're doing this on a stage, if you know that you have a sample that's relatively flat and there's not much deviation in it, you can change the range to, like, minus 10 to plus 10. Because in that way in your map, it'll cut your map time down some, because it won't be checking quite as large as a range. It'll be checking a smaller range, which will make the autofocus operate faster. Extra images. Now, if you have a really big sample that you want to visualize and get an image of, this extra images, you can actually get a video image that is larger than the viewable range of your objective. This is a program to actually get you a mosaic. where the stage will move, take an image, move, take an image, move, take an image, and it pieces them all together into a much larger image. So you'll actually be able to image stuff that's outside of your field of view. Auto exposure, same thing we saw before in the options window. Like I said, a lot of these things get repeated around. And then down here's a button for heat detector. It's for when you want to shut the system down. To be honest, I really don't like using the heat detector button because it just, at least in the older versions of software, it just kind of just goes, it seems to go slower, and it doesn't really update you or notify you when it's done, and you really don't know when the detector's warm and safe to shut off. I just like using the actual detector temperature window and just manually heating the detector myself, because then you can monitor how fast it's heating and how fast it's cooling. Next over is the video tab. The video tab is used by us for when we calibrate and align the instrument. It sets the parameters for the video windows, the responses for the video cameras, the video scales. You shouldn't touch the video tab. Nothing good will come of it. Next over is a setup window. This is the setup window that the students will be using to do their calibration. There's an instrument init icon, which on this particular product line really doesn't do much. It would only move probably the two motors that you have on the notch filter and the motorized mirror, and that's it. It's more important on our other Aramis-based system because that whole system is all full of motors. So this icon would be really important for that. But under setup here, we'll have instrument calibration. This is the window that you guys would use to check when you need to recalibrate your system to do a 2-point calibration. The system is light sensitive, vibration sensitive, and temperature sensitive. So if you come in one day and it's the hottest day of the year and the AC is not working that right, you'll notice that all of your data will have shifted. You'll get a linear shift as the room either heats up or cools down. So to do that, to do the 2-point calibration, the first thing you would do is you would go to 0 nanometers and check the laser line. And you would alter the laser line position by using the 0 coef here. If the laser is a little high, a little low, you just slightly alter the number here for 0, and you click apply, and you will see the peak shift, left or right. And you would keep changing it and applying until your 0 peak fell on 0. Once it falls on 0, you would come down to spectrometer, click on the left arrow to re-zero the drive again, and acquire, make sure it's still at 0. Whenever going to 0 order, always click on the left arrow. Do not type in 0. When you click on the left arrow, the instrument goes to the 0 order stop switch. And then says, okay, I'm at 0, goes to a mechanical switch. When you type 0, the instrument just counts backwards the motor steps and goes, I'm close enough to 0. And you might be at like 0.2 or minus, 0.3. But the instrument goes, that's 0. You can see it in the middle. That's good. So for calibration, always click on the left arrow to bring to 0. So once you are sure that your 0 laser line is actually on 0, because that is the start point for all the calculations. So if that is not right, none of your peaks will be in the right position. After that, then there is a coef adjustment for a spectral peak. So you would go to one peak that you know the position of, whether it be a neon line, or we have the silicon wafer, which comes with the system, which we use. Position of silicon 520.6. There's also hospital grade baby aspirin on there and polymer. So we usually use the silicon line. We would go to 520.6 wave numbers. And then if the peak was not on 520.6 wave numbers, we would alter this coefficient until it is. Okay. Every time you make a change in the coefficient, you must click on the apply button for the coefficient to take effect. You only want to change the last 3 digits in the coefficient. If you think that you need to be changing digits that are on the front half of the coefficient, you have much bigger problems and should not change it. Always, before altering the 0 or the coef, always write down the numbers on a piece of paper, because it's very easy to be doing something, you move, and then you hit backspace on the keyboard, and the whole coefficient is gone, and then you have no clue what it was. So I always recommend the systems you keep a logbook where you write down what the last coefficients were, just in case they ever get deleted.